Hi, this is Alex from devstories.eu, Learning DSPy, Episode 7 of 15. You cannot consistently improve what you cannot measure, and when dealing with language models, relying on human intuition to measure output quality simply does not scale. To automatically rewrite your prompts or tune your system, the compiler needs a mathematical guiding star, and that is exactly what defining success with metrics provides. In DSPy, a metric is a standard Python function. It takes two primary arguments. The first is an example, which represents the gold standard input and expected output from your dataset. The second is a prediction, which is the actual response generated by your DSPy program. The metric function compares the prediction against the example and returns a score. This score is usually a float, an integer, or a simple Boolean value like true or false. For basic classification tasks, your metric might be straightforward Python logic. You could write an exact match function that checks if the predicted string perfectly equals the expected string. To execute this measurement systematically across your data, DSPy provides a built-in utility called evaluate. You pass this utility your development dataset, your metric function, and execution parameters like the number of parallel threads. The evaluate utility runs your metric over every prediction, aggregates the results, and returns a single numerical score representing your overall system performance. However, exact matching is almost always too rigid for generative language tasks. This is where you transition from simple string checks to using AI feedback, a pattern commonly known as LLM as a judge. Because DSPy modules are just Python code, your metric function can instantiate and call a smaller separate DSPy program to grade complex semantic outputs. Consider a concrete scenario. You are building a system that generates a promotional tweet to answer a user question. An exact match metric fails completely here because a good tweet can be phrased in countless valid ways. Instead, your metric function should evaluate multiple dimensions of the output. First, it uses a basic Python length check to ensure the generated text is under 280 characters. Second, it checks if the text contains the factual answer required by the example. Finally, it passes the generated text to a specialized DSPy signature that asks a smaller language model to assess if the tweet is engaging. Your metric function then combines the length check, the fact check, and the language model engagement score into one final mathematical value. When you eventually start compiling and optimizing these programs, your metric function must accept a third, optional argument. It is called trace. Listeners often confuse the trace argument with a debugging log that prints out console errors or execution history. That is what it is not. The trace argument is a specific object used by the DSPy compiler during optimization to validate intermediate reasoning steps. If your program chains multiple language model calls together, the trace contains the specific reasoning path the model took to reach the end. By accessing the trace inside your metric, your function can verify not just that the final tweet was good, but that the intermediate steps used to draft it were logically sound. This is the part that matters. Your metric strictly defines what success looks like, and the DSPy compiler will ruthlessly optimize your system to maximize that specific score. If your metric is flawed, your compiled program will be flawed in exactly the same way. Thanks for listening. Happy coding, everyone.